So welcome to another session of Everyday Mathematics. Now today's problem comes from MIT 2024 Integration Bee Quarterfinals number 2, problem number 2, which is the definite integral from x equals to 0 to x equals to 1 of the natural logarithm or natural log of 1 plus x squared plus x cubed plus x to the power 4 plus x to the power 5 plus x to the power 6 plus x to the power 7 plus x to the power 9 plus bracket over x. So this is a very interesting problem. Before I jump into the solution to this problem, I'd like to thank our subscribers. Thank you so much for the support you give us. Your support really means a lot to us, and we don't take it for granted. For first-time visitors here at Everyday Mathematics, what we do is we go around and about and look for interesting problems, and we come back to you, share with you some of the solutions that we think befit these problems. And then to our repeating visitors who haven't subscribed, we do really encourage you to subscribe to our channels. So as I said, this is a very interesting problem. And the first thing I personally would like to do is to factorize whatever is under the log function. So 1 plus x squared plus x to the power 3 plus x to the power 4 plus x to the power 5 plus x to the power 6 plus x to the power 7 plus x to the power 9 can be factorized as follows. So I'd like to pair up some of these terms. 1 and x squared, these are the lowest terms, so I'll keep them like that. X to the power 3 and x to the power 5, I could pair those so that when I factor out x to the power 3, I get 1 plus x to the power 2 or 1 plus x squared. And then x to the power 4 and x to the power 6 could also be paired together, so that when we factorize x to the power 4, we still get 1 plus x squared, and x plus 7 and x to the power 9 and x to the power 9 could also be paired together, so that when you factor out x to the power 7, you still get 1 plus x squared. So then you go forward and then you do what we actually said. We pair these two, we pair these two, we pair these two. And then going forward, I pulled out x to the power 3 here, I pull out x to the power 4 here, I pull out x to the power 7. And then with these first two terms, I can factorize them by saying 1 plus x squared pulled out, we have 1 plus x cubed. That's the other factor that we can now multiply to that. And then here, when we pull out x to the power 4 plus x plus 4 and 1 plus x squared, we get 1 plus x to the power 3 left out, so we can keep that as another factor. So as you can see, we can factor this out, and then what we're left is 1 plus x squared times 1 plus x to the power 3 times 1 plus x to the power 4. This is what you get by factorization of this very long complex looking expression. So after that, now we can say that our integration now is simply the integration from x equals to 0 to x equals to 1 of the natural logarithm of the product of 1 plus x squared and 1 plus x cubed and 1 plus x to the power 4, all divided by x. And we can go forward and say, okay, let's use the rules of logarithm, where if you have a product of elements under the log function, that's the same as the independent summation of the log of these independent elements. So for example, for 1 plus x squared, 1 plus x cubed, 1 plus x to the power 4, that all being under the log function can be expressed as log 1x plus x squared plus log 1 plus x cubed plus log 1 plus x to the power 4. And then obviously we can divide each by whatever was in the denominator, which is x. So our problem now has become a problem that involves solving three different integrals. Log 1 plus x squared over x, log 1 plus x cubed over x, log 1 plus x to the power 4 all over x. So just to make things interesting, I've color-coded these different integrals into blue, green, and purple respectively. Now let's focus on the first blue integral, which is the log integral from x equals to 0 to x equals to 1 of the log of 1 plus x squared all under x. Let's try to integrate that. So the first thing I'll do is I'll say let y be equal to log 1 plus x squared. And so e to the power y is equals to 1 plus x squared, and therefore e to the power y dy dx is equals to 2x, so that e to the power y over 2x dy dx is equals to 1, and therefore ey over 2x dy could be substituted for dx. Now we can express the x on the left-hand side in terms of y. As you can see here, ey minus 1 square root would be the same as x. So ey over 2 times square root of e to the power y minus 1, all times dy could be substituted for dx. Now, as you can see, if we've substituted y for log 1 plus x squared when x equals to 0, we have log 1, and log 1 is 0. And then when x equals to 1, 1 plus 1 squared is 2. Therefore, y would be log 2. Therefore, the integration from x equals to 0 to x equals to 1 of the natural logarithm of 1 plus x squared over x is the same as the integral from y equals to 0 to y equals to a natural logarithm of 2 of y over square root of e to the power y minus 1 times e to the power y over 2, the square root times the square root of e to the power y minus 1. So this can be simplified further. And so we have pulling these two in the denominator out, we have a half times the integral from y equals to 0 to y equals to natural logarithm of 2 of y times e to the power y over e to the power y minus 1. Now, this part here can be expressed as the derivative of the natural logarithm of e to the power y minus 1, right? So that if we use our integration by parts, where if we have a integral of capital U dv, that's the same as the integral of capital U, it is the same as capital U times capital V minus the integral of capital V times the derivative of capital U, okay? So here our v is log e to the power y minus 1. So therefore uv is this y times that log e to the power y minus 1. Definitely applying the limits as required, minus the integral from y equals to 0 to natural logarithm of 2. And so v being log e to the power y minus 1, we keep it there. And then du, since u is 1, du is therefore just 1. And so this is what is left. Now, going forward, the upper limit, limit as y tends to log 2 of y log e to the power y minus 1 at log 2. Therefore, these functions are continuous. And we see that we can separate this as the limit as y tends to log 2 of y times the limit as y tends to log 2 of log y minus 1, and that y tending to log 2, y equals to log 2. At this point, we have log 2 here, but here, e to the power log 2 is the same as 2. 2 minus 1 is 1. Log of 1 is 0. So this upper limit would tend to 0. Same thing here. At the y equals to 0, we have this also tending to 0. And that is just self-explanatory. Okay, so we are left with the integral of negative, the integral of 0 from y equals to 0 to y equals to log 2 of the natural logarithm of e to the power y minus 1. And a half is kept out there. So now with this integral, we could say like let u be equal to log of e to the power y minus 1, and therefore e to the power u is e to the power y minus 1, and e to the power u du dy is equals to e to the power y, and therefore e to the power u over e to the power y. This is the same as, so e to the power y is the same as e to the power u plus 1 from here. And so e to the power u over e to the power u plus 1 du dy is equals to 1. And therefore you could substitute for dy with e to the power u over e to the power u plus 1 du. And so our integral here becomes half minus, as we know at 0, u tends to infinity since this becomes 1 minus negative infinity since it becomes 1 minus 1, and as this part tends to 0, the log of that would tend to negative infinity, and that's log to the power 2 would have 0. So we have, in place of log e to the power y minus 1, we have u, and then in place of dy, we put e to the power u over e to the power u plus 1, right? And then one thing we could do is with this sign, to remove this sign, we could just flip the limits. And then we could say let u be equal to negative u, and that would mean that where u is, we have a negative, such that this upper limit becomes positive. So the negative in this u and the negative with the u cancel out, so we have a positive, and then wherever you see a u, you get a negative or a reverse sign. And so we have now a half times the integral from u equals to 0 to u equals to u tending to infinity of u times e to the power negative u over 1 plus e to the power negative u. And so this could also be expressed as negative minus 1 minus negative, like that. So that now we could express this as a geometrical series. So we have negative and we have this summation. Now we have put this negative here because we considered this e to the power negative u negative as the first term of the geometric series. And so when we put this negative here in this sum, we must put a negative here because this is positive. So we have a half times the integral from u equals to 0 to infinity of negative u summation of negative 1, since this negative here now, negative 1 to the power k times e to the power negative k to the power u, where e to the power u is the common ratio that when put into a geometric series and sum to infinity, you would get this expression. So we go forward, and then we put this u into the integral and take the integral into the summation sign. And this is easy. This is trivial because if you have a series or if you have a sum of expressions and you try to integrate it, it's the same as integrating each specific term independently. And so that's what we've done. We've gone to integrate each independent item in the sum. And since we have this negative here, this expression is the same as u times the derivative 1 over k e to the power negative k to the power u. E to the power negative ku. And so using integration by parts, this being v, and so it's being capital U, so uv is therefore the product of these two. with the limits applied appropriately, minus, and keeping this as v, and then du being 1, since this is u, so derivative of this small u with respect to u is just going to be 1. And so continuing further, we do have a negative 1 to the power k there, limit as u tends to infinity of u to the power u over k times e to the power negative ku, minus limit as u tends to 0 of u over k times e to the power negative ku. So the interesting thing here is if you express this in terms of 1 over k, u over k, u over k to the power, u over e to the power ku, using L'Hopital rule, since both will tend to infinity, both numerator and denominator, you could differentiate the numerator and the denominator respectively, and then the first derivative with the limit tending to infinity, as you can see, the u with respect to u when differentiated becomes 1, and this becomes negative k times e to the power k u. So the numerator tends to infinity, and the entire thing tends to 0. So this tends to 0. And with this is trivial, since u tends to 0. This also tends to 0. And so we left. So as we said, these initial terms go to 0, and this tends to 0. And so we're left with a summation, half the summation from k equals to 1 to infinity of negative 1 to the power k in bracket negative 1 over k, integral from x equals to, u equals to 0 to u tending to infinity over the power negative k u du. So when we integrate e to the power negative ku, we have a negative 1 over k e to the power negative ku, but that negative and this negative cancel out, so we are left with just the positive terms. Now when we apply the limits, as you can see here from the upper limit, when u is tending to infinity, this tends to 0. This tends to 0. So we are left with a negative we're left with a negative 1 over k squared times negative 1 to the power k. And that means that the odd terms, since this essentially becomes negative 1 k plus 1 times 1 over k squared, right? So what this means is that the odd terms are positive and the even terms are negative, right? Obviously times half here. So how do we solve that? Now we resort to what is called the Basel problem. The Basel problem states that when you have 1 over k squared sum from 1 to infinity, that results to pi squared over 6. Now, when we have this, we could separate this into the odd and the even terms. And then with the even terms, you can pull 1 over 4 out, and you still are left with 1 over 1 squared plus 1 over 2 squared all the way. So you're left with still the Basel sum here. So that the Basel sum is equal to the odd terms plus a quarter, the same sum. And so when you subtract both sides, we are left with 3/4. The Basel sum is equal to the odd terms. And so that means that you divide, you multiply 3/4 by pi over 6. And so the odd terms is equal to 3 pi squared over 24, since 3/4 times pi over 6 is the same as 3 quarters times pi squared over 6 is the same as 3 over 24 pi squared. Now, the remainder quarter, a quarter of the pi squared, I beg your pardon, so I made a mistake here. So what this means is that sorry, just this here is not entirely correct, right? But we could say that the even terms, since odd plus even is equals to pi squared over 6. And we know that the odd is 3 pi over 6. 3 pi squared over 24 plus the even is equals to squared over 6. And so even is equals to pi over 6 minus 3 pi squared over 24. So pi squared over 6 is the same as 4 over 24 pi squared, and so 4 minus 3 is pi squared over 24. Actually, we are correct. This expression is correct, so we can go ahead and so this is also correct. So the even term adds up to pi squared over 24. Okay, and so when we go ahead and say now back to our problems of the integral from x equals to 0 to 1 of the natural logarithm of 1 plus x squared, all under over x is equals to a half negative the odd terms plus the even terms. So it's the other way around, positive, negative. So we have half the odd terms is 3 pi squared over 24 minus the even, which is pi squared over 24. And so 3 minus 1, so we have 2 pi squared over 24 times a half. This cancels out. And so here, the blue term amounts to pi squared over 24. Now the green terms, the integral from 0 to 1 of 1 plus x cubed over x, we could still say y is equals to log 1 plus x to the power 3. E to the power y is equals to 1 plus x cubed. And so ey dy dx is 3x squared. And so ey over 3x squared dy dx is equals to 1. And so x squared is the same as e to the power y minus 1 cube root squared. And so this is it. So when x equals to 0, same thing, y is equals to 0. When x equals to 1, same thing, log y is equals to log 2. And so our integral here becomes integral from y equals to 0 to log 2 of y over e to the power y minus 1 over x, which is e to the power y minus 1 cube root times, in place of dx, we have e to the power y over 3 times e to the power y minus 1 to the power 2 over 3. And so you multiply that together, you get a third times the integral from y is equals to 0 to y equals to log 2 of e of y times e to the power y over e to the power y minus 1. Now, since from the previous blue term you saw that this first term is equal to 2 pi squared over 24, and that is, in other words, the odd minus the even Basel terms. And so it means that since this is a third of that, we have a third of that is a third times 2 pi squared over 24, which is pi squared over 36. Same thing for log 1 plus x to the power 4. You do the same process and you realize that the integral is the same as a quarter of the integral from y equals to 0 to y equals to log 2 of y to the y times e to the power y over y e to the power y minus 1. So, and since we know that this integral alone is the same as 2 pi squared over 24, and we can say that now purple integral is a quarter times 2 pi squared over 24, which is pi squared over 48. So the final integral is the blue plus green plus the purple. And we saw that the blue is pi squared over 24, the green is pi squared over 36, the purple is pi squared over 48. The common, the LCM, the lowest common multiple would be 144. 144 divided by 24 is 6 pi squared now. 144 divided by 36 is 4. And then 144 divided by 48 is 3. So add this up, we get 13 pi squared over 44. So this is the final answer for the integral here from x equals to 0 to x equals to 1 of the natural logarithm of 1 plus x squared plus x cubed plus x to the power 4 plus x to the power 5 plus x to the power 6 plus x to the power x to the power 7 plus x to the power 9 all over x. So this is the answer. The few things that we've learned along the way is that the integral from x equals to 0 to x equals to 1 of natural logarithm of 1 plus x squared over x is equals to a half. The integral from y equals to 0 to y equals to log 2 of e to the power of y times e to the power y all over e to the power y minus 1. And then when this shifts to x to the power 3, this becomes a third, but the expression, the integral is the same. And then when this shifts to 4, this becomes a quarter. And so we could say generally, the integral from x equals to 0 to x equals to 1 of natural logarithm of 1 plus x to the power n over x is equals to 1 over n times the integral from y equals to 0 to natural logarithm of 2 y times e to the power y over e to the power y minus 1, right? And that is the same as 1 over n times pi squared over 12. And for this to be 1, this means this n is 1. So this is an interesting something to remember. I don't like memorizing formulas, but I think it's something that one would memorize. But it's a very interesting tool. Very, very interesting. So thank you very much. Thank you very much for those of you who've been following along. If you have any question, please don't hesitate to leave us a comment. Or if you have an alternative method that is shorter, that is more interesting, please don't hesitate to share with us. We are here to learn, we're here to share, we're here to grow. Thank you. Until next time, bye-bye.